Okay, so there's a couple of things, guys, we have to realize when we're coming across a work energy theorem question. Okay, so there's kind of a checklist that you want to go through, okay, that'll enable you to be as successful as possible when you're dealing with one of these. All right? First thing is always to do what when you encounter one of these questions? Write down your givens. Okay? Okay, and we do that with any kind of problem-solving question. So, okay, that's not even really the first step. It's just something we always do. All right, but the first step for a work energy theorem question, once you have the givens written down, is it possible then to tell which kind of energy is changing? Okay, what are the two kinds of energy that we dealt with? Potential, gravitational potential energy, and kinetic energy. All right. Now, are they both affected by different things? Okay. Gravitational potential energy is affected by what three things? Mass, gravity, and height. All right. Those are the three things that affect gravitational potential energy. So if the work I'm doing in a work energy theorem question results in the object getting higher above the ground without changing its speed, am I changing gravitational potential energy? Yes. Okay. And once we realize what kind of energy is being changed in the question, solving the problem becomes fairly easy, because then you know what formula to set work equal to. All right. Does everyone follow me there? Remembering that work obviously is a change in energy, which means force times distance is a change in energy. And all we have to do then is identify what energy is changing. All right. Now, this set of steps is okay for Science 10, where you only ever deal with one kind of energy changing at a time. Okay? But in Physics 20, you will deal with questions where mechanical energy changes, which means not only does the object's gravitational potential energy change, its kinetic energy changes as well. All right? Now, it's not really a lot different. It's just that you have to calculate both at the same time. Okay? But for us, for simplification purposes, okay, our first step is to identify what kind of energy is changing. Okay, and whether that's, EP, so MGH, or EK. Okay, if kinetic energy is changing, what about the object will be changing? Its speed, yeah. Okay, its speed will be changing. Right? If I'm changing the kinetic energy of an object, then I have to change how fast it is going. Right? Because I can't change its mass. I suppose the other way to change the energy of an object would be to give it more mass, but really that's kind of not what we're looking at here. Okay? That's changing the object as opposed to changing the object's energy. All right, once we've identified the type of energy that's changing, then we set up work energy theorem. Okay, and what I mean by that is this. I mean that work is a change in energy, and that means force times distance equals final energy minus initial energy. Okay, so at that point, that could mean one of two things. Okay, it could mean that force times distance equals 1/2 mvf squared minus 1/2 mvi squared, or it could mean that force times distance equaled m times g times hf minus m times g times hi. It depends whether gravitational potential energy is changing or kinetic energy is changing. Minus. Sorry, minus. Right? Because it's change. This is minus 2. Julia? Yes, that's supposed to be a squared, but it didn't look right, and then I scribbled it, and it looked even worse. Squared. Still looks bad. MVF. Okay, yeah, okay. So I know my penmanship is bad. 1/2 MVF squared, right? Final velocity, because that would represent the final kinetic energy. Everyone follow? Okay, and then this is 1/2 MVI, the initial velocity or initial speed. Okay, that would give me the initial kinetic energy. That helps me calculate the change in the kinetic energy of that object. And it's the same idea over here. M times G times the final height minus M times G times the initial height. That gives me the change in gravitational potential energy. Okay. So, in a question like this, I mean, now it depends, what did the question ask us to calculate? Did it ask us for force? Did it ask us for distance? Did it ask us for one of these speeds? Okay. But from here, can we calculate anything else? Right, if I wanted to calculate VF, could I add M1/2 MVI over to here, okay, and then start manipulating some more? Right? As long as we get to this step, where we've set up that work is equal to a change in energy, we should be able to solve for any part of that equation. All right, and that's what you're going to be asked to do more often than not. And in fact, more often than not, okay, in these kind of questions, either the initial energy or the final energy is going to be 0. Right? I mean, on Friday, did any of the examples we have not have an initial energy or final energy? One or the other is 0. Okay? They all started or ended at 0. Okay? Which makes that quite a bit easier, because then you can cancel off one of the two of these, right? Either the final or the initial is 0. Okay? Ringing a bell? All right. So the third step then is, okay, manipulate and solve the equation. Okay, I want you to try that one. Okay, write it down. Okay, give it a try. I'll give you a couple minutes. Okay, so on this one here, we've got something being lifted 1.5 meters. What kind of energy is changing? Gravitational potential energy. All right, so it's being lifted. Okay, we'll assume from the ground, because that's usually where you measure height from. Agreed? So what was its initial height? How much gravitational potential energy does it have there? 0. All right, so let's write our givens down here. Okay, we know that the initial height was 0 meters. Okay, we know that the final height was 1.5 meters. We know the mass was 50 kilograms. Okay, and yeah, so we're good with that. All right, so if work is a change in energy, okay, we've got force times distance equals m times g times h f minus m times g times hi, which was going to be anyway 0. All right, so I'm going to leave it at this. Here's the trick for this question. The height's 1.5 meters. Over what distance did I apply the force? 1.5 meters is the trick. This has also, okay, has to be the distance over which I applied the force in this question. All right, would you agree? If you lift something, you're lifting it straight up, which means your force is directed in exactly the same direction, okay, as the energy being changed. So we have F, okay, sorry, we're trying to solve for F. So F is going to equal then M times G times HF over D, okay, which essentially, can I do this if they're the same number? Right, can I cancel them? It doesn't matter. If you didn't cancel them and you put 1.5 in on both the top and the bottom, it canceled itself when you calculated it, but okay, works out. So F equals M times G. All we have to do then is go 50 times 9.81. Which should give us 490.5, right? And the units for force are newtons. All right, so that one's a little bit tricky. I probably wouldn't give you one like that on a test just because it would throw some people. Okay. Questions on that one? All right. I want you to try this one. We talked about this on Friday, and we talked about how lifting something to the top of a ramp is no different than pushing it up the ramp in terms of the amount of work that is done. All right, so I want you guys to see if you can figure out the height of this ramp, okay, using the work energy theorem. So, since the speed of this thing isn't changing as it gets pushed up the ramp, what kind of energy am I changing about it? Potential energy, right? I'm changing the height of the box. So if I know the force I exert and the distance over which I exert it, I can figure out how much the energy changes by, given that the bottom of the ramp would be a height of 0. Okay, so the force we're told here is 150 newtons. Okay, and the distance is 25 meters. And we know that G is 9.81, and we know the mass of the box, 35 kilograms. Okay, so work is a change in energy. So force times distance equals m times g times hf minus m times g times hi. And since it started at the bottom of the ramp, m times g times hi is 0. All right, so I'm just going to eliminate that and not bother writing it. All right, I need to solve for hf. How do I get hf by itself? Divide each side by mg. Okay, so now we can plug in our numbers here. 150 times 25 over 35 times 9.81. And that should give us 10.9 meters. All right, does that make sense, guys? Okay. I'm not belittling your intelligence by doing so many examples, am I? Julia? Could you do Pythagorean theorem? You only know one side of the triangle. Well, that's c squared, but you got to have at least one other side. You can't have a triangle with a side that has 0, otherwise you have a two-sided object. Does that make sense? I mean, if you knew the height, yeah, you could, but then that's what you were looking for. The answer is, if you were given enough information, yes, because it is a triangle, you could use Pythagorean theorem, but in this case, it's not one where you could do that. All right, give this one a try. This one has to do with what kind of energy? Yeah, kinetic. It's changing the speed of the baseball this time. Initial. Okay, change is always final minus initial. So, since this person is pitching something, usually when you start pitching, how fast is the ball moving? 0. Okay, doesn't have any kinetic energy at the beginning of this question. All right, it's in his glove. It's not moving. All right, at the end of the question, after he's been exerting 300 newtons of force over a 2.2 meter path, okay, then the ball has some energy. All right, so again, we have to go back to this. Work is a change in energy. Okay, that's what it's always going to come down to. So our givens are this. Okay, we have a force of 300 newtons. We have a distance over which it was exerted of 2.2 meters. And we know that the mass of the ball is 0.250 kilograms. All right, so work is a change in energy. So force times distance equals 1/2 times the mass of the baseball times the final speed of the baseball squared minus 1/2 times the mass of the baseball times the initial speed of the baseball squared. What does that come out to? 0, because there was no initial speed for the baseball. MJ? I'm sure it isn't. Because that's what the work energy theorem is, and you would probably get a mark for it on a test. It's a method mark. Yeah. Okay. Because when we get to the exam time, you'll have other questions that deal with energy. And being able to discern whether it's a work energy theorem question or a conservation of energy question is worth a mark. Right? And so that's why I'm doing that now. Okay, I know it seems kind of redundant, but that's why. Is later on when you identify that's that kind of question, that's a mark. Okay. All right, so this is 0, so I'm just going to eliminate it right now because it didn't have any initial kinetic energy. So now that I know that force times distance equals kinetic energy, can I solve for the speed? Okay, what do I have to do with half an m? Divide them, right? Take them over to the other side so that they're out of the way. Okay, do I want v to be squared or not squared? Not squared, so what do I have to do to both sides? Square root. Alright, so when we do that, we're going to be left with this. The square root of 300 newtons times 2.2 meters over 1/2 times 0.250, all square rooted. Okay, and that should give me 72.7 meters per second, right? Now, in case you need to see what that looks like on your calculator, right, remember that I said you could do this either using lots and lots of brackets or you could do it piecemeal. Again, probably piecemeal is probably the best way. So 300 times 2.2, okay, gives me 660. Okay, divide that by 0.5 times 0.250. Okay, why did I put that in brackets? Does it make a difference if it goes from left to right or if it does the bottom first by the top? It makes a difference. Okay, I want the top divided by the entire bottom, not the top divided by 1/2 and then multiplied by 0.25. It's not the same thing. Okay. All right, gives me 5,280. Now I need to square root that. So second square root, get the answer in there. All right, I get 72.7 meters per second. Okay, if you wanted to do that all in one step, you can just go like this. So 300 times 2.2 over 0.5 times 0.250. It's not enough brackets. I want more bracket. There we go. Okay, so it'll work. It's just you got to keep track of brackets. Even I screwed that one up. I had one extra set of brackets. But as long as you close everything off, it's all good. Okay. Starting to make a little bit more sense, guys? Do they all work essentially the same way? They all start out with final energy minus initial energy equals force times distance. And that's not going to change. I'm not going to try and trick you on a unit exam or a quiz by giving you something that works differently. Okay? They all pretty much work that way. The trick is it potential energy or kinetic energy that's changing? All right, so I'm going to give you the worksheet here and let you guys try some of those, okay? And then we'll go through as many of them as we need to go through. We'll go through because this is, like I say, probably the most important thing you learn in high school science. Okay, let's just take a quick look at 1 and 2 here, just okay, for argument's sake. So on number 1, sometimes a question is actually a lot simpler, okay, than we maybe initially think it is. For example, do you need to do work as a change in energy for this question? No. But work is also force times distance, agreed? Were you given a force and a distance in this question? Yeah, okay. And since it didn't ask you for height or force or whatever, all you had to do was go force times distance and get work. All right, so the big thing there is when we write down our given says, okay, calculate the amount of work done. Okay, so work is what I'm looking for. Okay, force was 32.0 newtons, and I'm given something in meters here. Well, that can be a distance or a height. Okay, but I'm going to make it like that. All right, force times distance is 96 joules. Now, when you do work, okay, you change energy, agreed? All right, and so in that question, did you actually have to do any calculating for B? If you did, it's because you didn't understand that work is a change in energy. Okay, and I'm not saying that that's bad or that you're that you're not intelligent, but it's just a matter of that's the understanding we have to get to. I told you on Friday, it's really easy for us to say, oh yeah, work's a change in energy. I remember that. There's a difference between remembering it and applying it. This is a question where you apply that. If you understand that if you did 96 joules of work, that changed the potential energy of the box by 96 joules. Okay, then you're getting the work energy theorem. Right? If you went m times g times h or tried to figure out how to do that, okay, you did a lot more work than you probably needed to do. Okay, is that making a little bit of sense? Okay? If I do work, I change the energy of something. Okay? And I change it by the amount of work I did. Now for number 2, all right, if an object gains 155 joules of potential energy, is a gain a change? Okay, so that's the change in energy. Is that also then the work done? Yes, it is. So they told me the work in that question. They told me the work was 155 joules, okay, and it was lifted 1.2 meters above the Earth. Can I calculate the force? Yeah, work is force times distance. Okay, so all I have to do then is divide both sides by d, and I've got F. All right, so again, these questions mathematically are simple, but they're testing whether we can apply our knowledge of work being a change in energy. Nathan, question? 6? Yeah. All right, so on this one here, I'll just erase all the work I've done here so that we can set it all up. All right, so we got a mass of 0.02. Okay, it has 320 joules of kinetic energy. How fast is it going? Does it ask me anything about work here? Okay, so this isn't a work question, is it? It deals with kinetic energy. What's the formula for kinetic energy? 1/2 mv squared, right? So this is, again, why it's so important to write down our givens. M, EK, and V. I only got one formula on that formula sheet that has those 3 things in it, agreed? Okay, and that's that one. So now I can solve for how fast is it going. Okay, so I divide both sides by 1/2 of m. Okay, and then square root to get rid of the square there. Plug in my numbers. So 320 over 1/2 times 0.02. Okay, and when you square root that, you should get 178.9 meters per second. That is not a rubber band you'd want to get in the eye. Seems to work out for me. Are you bracketing properly? Okay. Because if you don't enclose the bottom in brackets, it does it out of order. Well, it does it in the right order, but not the order you want. Okay, because I don't want it to divide 320 by 0.5 and then multiply by 0.02. I want it to divide by 1/2 of 0.02. Okay, and it makes a difference. Okay, any other ones you want to go over there, guys? Don't be afraid to ask. Okay, well, if more come up, just ask. All right, so on number 7 here, we've got a force of 100 newtons, and we're drawing a bow back 0.29 meters. And remember I told you, like, bow and arrow and slingshot questions are my favorite kind of questions to use on both exams and quizzes. Okay, we're looking at what speed the arrow will leave the bow at. So what kind of energy is the work I'm going to do going to become for the arrow? Kinetic, right? If I'm asked to find a speed, it's not asking me about potential energy, is it? All right, so I want to say then that the work I do is going to become the final kinetic energy of the arrow. Because I'm going to assume that while it is sitting in the bow drawn, it is not moving and thus has 0 energy. Is everyone okay with that so far? All right, so I'm solving for speed here. So I'm simply dividing both sides by 1/2 of m. Okay, and that then square rooting that to get VF. All right, so when we plug in our numbers here, that's going to be 100 times 0.29 over 1/2 times 0.120. Okay, when we do that, we should get 22 meters per second, but we'll just double check. Okay, so 22. Okay. I would expect something similar to that tomorrow on your quiz, because I lack creativity and I like these kind of questions. Hint, hint. Yeah. All right, any other ones there, guys? All right, if you're not getting it, don't panic. We are going to be working on this most of the week. We'll probably do a lab tomorrow, okay, stuff like that. So we are going to spend a fair amount of time on it, okay? And I was looking at dates for your unit exam as well. And I hadn't found one for sure yet, but you can bet it's going to be late second week or early third week of December. All right, so either late next week or early the last week of December. All right, I will let you know. I'll put it up probably today at some point. It'll be up on Twitter and on the website, so you can check there. Okay, I'm just going to say it's going to be the 16th, guys. Okay, December 16th is going to be the unit exam. We'll definitely be finished by then. All right, so we may even have started the next unit before then, but we'll say it's the 16th, so you have exactly 2 weeks' notice. Okay.